is the classification of electric vehicle charger time series with selective clustering. That will be delivered by Tongxin Li, who is pursuing his PhD at Caltech, California, USA. He received a BSc in mathematics and a second BSc in information technology, both of them from the Chinese University of Hong Kong. His research interests focus on problems arising in electric grids and theoretical machine learning. Please start your presentation.
All right, thanks for the introduction. I'm Tongxin Li, a third-year PhD student from Caltech. I will be giving a presentation on classification of EV charging time series. This is a joint work with Chenxi, Stephen, and Victor. As we all have been aware that nowadays, EV charging is playing an increasingly important role in our daily life as the global EV market continues to grow. According to IEA, the global EV stock will exceed 130 million by 2030. Since EV charging can reduce greenhouse gas emissions, it can help tackle climate change problems and realize sustainability. In our study, we use the ACN data, which is a dynamic data set collected from adaptive charging networks. In this data set, there are more than 32,000 EV charging sessions available, and keeps growing with around 90 sessions being uploaded daily. It contains the following information: connection time, which is the time when the EV plugged in; disconnection time, which is the time when an EV unplugged; kilowatt delivered, which is the energy delivered during the session; and user ID, which is a unique identifier for the user. Besides the discrete session information, it also has two sides of fine-grained time series data corresponding to the pilot signal, which is a time series of the charging signals used by the controller, and is the current that the controller would like a particular EV to be charged with. And another is the actual charging current, which is the time series of the measured current of the EVSE during the session. The pilot signal and the actual charging current may differ from each other, and I will show you some examples and explain the reasons in later slides. The real EV charging data collected from the charging infrastructure contains rich information that allows us to better understand and design intelligent EV charging systems. In this work, we focus on the following question: what can we learn from the EV charging time series about the actual charging behavior? Well, the whole picture of our work is as follows. Our goal is to learn a set of representative charging patterns from the time series data. After doing this, the learned charging types can be used for downstream applications such as charging behavior prediction or charging stage decision. We'll go into the details of the applications later. So what are the challenges of getting a good characterization of types? The first is that we have no labeled data for doing this classification, and user ID may not be a good partition of types because there may be hundreds of users, but only a few of the numbers of charging patterns. Moreover, a registered user may have two different EVs or simply can buy a new car. All of these make classifying using user ID impossible. So why wouldn't we just use the car model information? Well, this is our second challenge because of privacy concerns, our data only has anonymous user ID labels, but we don't have access to the car models. So we have to do our classification in an unsupervised way. The last challenge is about the data itself. The charging time series can be very messy, so the time steps may not be perfectly aligned. For example, the charging curves can fluctuate a lot because of random noise, or the underlying scheduling algorithm can make the charging curves fluctuate. The charging curve also highly depends on user behavior. Customers can plug in or unplug regardless of the charging states, so the charging curve may not even represent the full charging cycle. Those are all practical issues that are very hard to solve in order to find the right information from the data. So then how can we really find the right classification from the messy data? Let's first take a look at a concrete charging curve. As mentioned earlier, we observed from data that the measured charging current doesn't follow the pilot signal exactly. Specifically, the mismatch may be due to the following reasons. First, the maximum charging current that the vehicle can take may be smaller than the control signal. And second, because of random noise. The last and so the last and third reason is that an EV really goes into the absorption stage so that its battery is about to be fully charged. The key observation is that the jump, because of the third reason, has a distinct pattern, which can be used for our classification. So we refer to the subsequence of the charging curve in the observation stage as a charging tau. Ideally, the current in a charging tau decreases steadily from the maximum charging current Cmax to 0. A key thing here is that the shape of this tau often has distinct patterns depending on the battery types of the EV. For example, the charging tau for Tesla may be different from that of a Nissan Leaf. So the charging tau can be used to classify the charging curve. However, real-world data is always messy. The consequence is that not all charging curves contain taus, which are very useful and distinctive features for doing the classification. In the data, certain batteries do not have a smooth absorption stage, and the current just drops from Cmax to 0 almost directly. In addition, EVs may be just unplugged before they are fully charged. So the drop in the current may not always be because of the internal battery state, meaning there is indeed a tau. So the drop could also be because the external reasons such as scattering or noise, as you can see from the three examples. This also poses challenges in finding charging taus. So how can we find the taus that can use for our classification? Here we introduce three rules for tau extraction. First, we can extract them by pilot signals. Since a tau is typically a decreasing sequence, we declare that the battery has entered the absorption stage if the charging current tau falls below a certain threshold and is not due to pilot signal. So the end of stage is the time when the charging current first reaches approximately 0. However, this rule is not robust to noise, since random noise may cause the charging current to drop below the threshold even before entering the observation stage. We can also extract taus by the duration of the observation stage at the end of the stage by locating the first 0 value of the charging currents. This approach requires knowledge of the tau duration. Moreover, even for the same battery, the duration of the observation stage varies across different sessions because of noise and the resampling of data. The third method assumes the charging taus from the same EV type have similar properties such as duration and type. Suppose a tau template is provided. We can use it to find the most similar subsequent from the charging curve, which is likely to be a charging tau. The figure on the right illustrates the idea. So the right subsequence is a template. The black vertical line indicates the best matching location in the charging curve for the template, and the tau can be found correspondingly despite the size difference of both taus. So how can we classify charging curves based on the pattern of its charging tau? Before we introduce our first approach, let's first revise the classic K-medoids clustering, which attempts to minimize the distance between points in a cluster and the point CK designated as the center of the cluster. In contrast to the K-means algorithm, K-medoids chooses data points as centers and can be used with arbitrary distances. For our clustering problem, we have another layer of freedom. That is, we can decide what taus to be extracted and considered in our clustering problem. So we can make use of this and go beyond the classic K-medoid clustering. Because we can choose taus, the objective we want to minimize further depends on what taus we choose. So we have an additional minimization atop of the original K-medoid objective. We minimize the sum of distances by choosing both the clustering and the set of n tau candidates. To solve the optimization, we use the idea of alternating minimization and refine the representative of each cluster by iteratively implementing the following until convergence. With suitable initialization, the iterations consist of two main steps. The first is a step for tau extraction. Given a fixed clustering, define a set of taus and minimize the cumulative distance. Next, With fixed tiles, we cluster them and refine the clustering by doing K-medoids. We can show that the proposed approach is guaranteed to have local convergence. It can be proved by noting that each iteration can only decrease the objective that we want to minimize. As a high-level overview, our approach can be described as follows. First, we collect the time series data as an input. Next, we pre-process the charting time series by resampling them as a min over fixed time interval and filling in the missing points by linear interpolation. This ensures the alignment of the signals in the time domain. Then we perform the first tile extraction rule with the help of pilot signals and the durations to obtain a set of initial charting tiles. After that, we cluster the charting tiles and use the medoid of each cluster as the new representative tiles to reperform the third rule of tile extraction by matching. We iteratively repeat these two steps until the objective converges. After converges, we obtain a set of representative charting tiles. In our experiments, the iteration converges really fast, just after a few steps like 3 or 5. In the experiments, we use similar based clustering techniques for test clustering. Tiles of different lengths are clustered by first constructing a similarity matrix and then doing spectral clustering. We compare 3 distance functions: Euclidean distance, modified Euclidean distance, and dynamic time wrapping. Euclidean distance has the shorter tile with zeros to make 2 tiles of the same length. Dynamic time wrapping is a widely used distance for measuring the distance between 2 sequences with different lengths, but the computational complexity is high. So we introduce another distance, which is the modified Euclidean distance. So roughly speaking, we penalize the mismatch of 2 tiles and the difference of their length. We evaluate the quality of the clustering by 2 metrics, Sahota coefficients and the percentage of correctly grouped charting curves. For the second error metric, we say a tile is correctly classified if it's clustered into a group, bringing the majority of the tiles have the same user ID as the tile being considered. It can be seen that k equals 6 is a good choice of number of clusters for this dataset, since it is the largest value at which all the tiles are correctly classified for both Euclidean distance and modified Euclidean distance. We visualize the clustering results of 6 clusters for the 3 distance functions. In the figure, tiles are within the same cluster if they have the same color, and the tile representatives, as known as the cluster of the medoids, are emphasized. It can be seen that using the modified Euclidean distance, the 6 clusters are well separated, and the corresponding medoids provide informative patterns for charting tiles. You can see the Euclidean distance blurs the charting tiles of shorter length, but using the modified Euclidean distance gives a high quality and efficient classification comparable to what dynamic time wrapping gives. So the figure shows a 2-dimensional TSNE visualization of our clustering results with 6 clusters. Tiles for different users are colored differently, and the marginal probabilities P1, P2, and P6 up to P6 represent the portions of charting sessions falling into the 6 clusters. Based on the classification, let's consider the downstream.
Excuse me, Tongxin, you have 2 minutes left.
Sure. Let's consider a downstream application of predicting the charting behavior of given session. We predict the charting tiles offline with the help of user ID. We can also do the same when there is no user ID available, but the results become worse, and if you're interested, you may check our paper for details. The table shows the accuracy of our prediction with user ID available, as can be observed from the results. Except for user 404 and user 651, the tile representatives of the other users can well predict the charting tile behavior for the coming sessions. So the figure on the right visualizes the training curve testing tiles and the tile representatives of 2 users, including the 2 users with high prediction error. Different from the normal users, the tiles for user 404 and 651 in the training data are very different from those in the testing data. And this inconsistency could happen because of for example, the user change their cars and so on. The charting tile can also be used for online decision. We use sequential time series data to determine whether an EV is in the opposition stage or not. This figure shows the trade-offs between the decision accuracy and the waiting time, or equivalent the number of samples, the number of data samples needed for the binary prediction. It can be seen that both the average precision and the average sensitivity grow with the number of samples. And that's all for my presentation. Thank you for your attention.
Thank you very much, Tongxin, for a very, very crisp, good presentation. You made a very complex topic look easy. Thank you. We don't seem to have questions waiting for you in the Q&A, but I do have a question that I would like to ask. The classification method which you present in figure 3 of your paper is iterative in nature, as you correctly as you mentioned it. Is it possible to talk about a rate of convergence in this case? You know, linear, quadratic, oscillatory. How would your algorithm converges?
So right. So far, we can show is local convergence.
Okay.
So we can only show, for example, the objective will converge to a certain value, but they don't have global convergence yet.
Okay. Thank you very much. We don't seem to have any other questions. As I said, it's a very interesting paper. It's not a topic not normally seen in the area of power systems, but I'm sure more and more of these kind of tools would come to be used. Thank you very much.